So now we're going to turn our attentions to energy and work, which will be related to energy. And to start here, I just want to get into an overview of energy. And although we've been talking about quantities being conserved, it's probably worth spending another moment to just explain what I mean by something being conserved. When a physicist says that a quantity is conserved, what they mean by that is that it remains constant through some process. So let's think about a fairly ridiculous example here. Let's say that Joe and Jane have been playing lots of D&D. And Joe notices that Jane's D20 seems to have the miraculous ability to roll a natural 20 whenever the party absolutely needs it. So Joe, thinking about how their campaign is going in a different group that they're a part of, decides to offer Jane $10 for this miraculous D20. Jane happily agrees with this because they know that it's actually just their absolutely amazing ability to throw the die just so that generates those natural 20s and could be done with any other die by the same manufacturer. So Jane happily sells the D20 to Joe. So we go and look at the contents of their wallet before the transaction. We see that Jane has $30 and Joe has $20. Now, afterwards, Joe's wallet is going to be $10 lighter, and Jane's wallet will have picked up $10. And so we can add this all up and get that both before and after they have $50 in their wallets between them. So a physicist would say that that wallet contents are conserved under exchange of magical D20s. Now that's a painfully contrived example, but it gets the point across. And I've mentioned Nether's theorem in the past. Emmy Nether demonstrated that for any symmetry in nature, there is a corresponding conservation law. And we've seen that momentum was a conserved quantity because the laws of physics are the same in every location. Turns out that there's another symmetry that we know of, actually several, but the next one that we know of is that the laws of physics must be the same at all times. Now, what this turns out to mean is that a quantity called the Hamiltonian remains a constant. And in almost all circumstances, what that amounts to is that energy is conserved. So, probably worth spending a moment then talking about what energy is. We can broadly break it into two categories. There will be kinetic energy. So this is associated with the motion of an object. And this energy is associated with motion of an object is always positive, or at least zero. Zero if it's not moving, and if it's moving, it's positive, and the faster it's moving, the bigger the number. Potential energy is a little more complicated. This turns out to be the energy is associated with the relative position of two objects and the conservative force by which they are interacting. So potential energy could be positive, negative, or zero. Those are all possible. It can depend on your choice of coordinates. So for instance, let's say you have two objects interacting under gravity, or let's say we're near the surface of the Earth. You can make the value of the potential energy for, say, a brick near the surface of the Earth any value you want it to be by deciding where you want y equals 0 to be. However, if you look at the beginning and the end of some process, the change in the potential energy will always be the same. So I've mentioned conservative force here, and we'll have to hold on that for a bit. I will give a more thorough definition of it. But for now, no friction, no air resistance, nothing that generates heat or noise. But we'll give a better definition later. So gravity is an example of a conservative force. Now, say if we are looking at a planet and a moon interacting, it'll turn out here that you sometimes run into a situation where the choice of coordinates is forced on you by the mathematics that was used to derive the relationship. And so in the case of gravitational potential energy, by the necessary choice of coordinates that you have to make, gravitational potential energies will always be negative if you're talking, say, between planets or something like that, where you have to use Newton's law of universal gravitation. But near the surface of the Earth, you have some freedom to choose your y coordinate. So sometimes you can choose your coordinates to make calculating potential energies a little easier. Other times that choice will be forced upon you, and I'll try to highlight that out. So just to give a bit of a feel for how this is going to go, the kinetic energy of a moving object is 1/2 mv squared. And we can write that the it's just K. And we can write that the gravitational potential energy of an object, we'll call that U sub G, is mgy if we're near the surface of the Earth. Now, in both of these cases, if you grind the units through, you'll find that you have kilogram meters squared per second squared. This shows up enough that gets its own special name, and we call it a joule, Joule. This turns out to be after the person who figured out that heat was actually energy in transfer. So Anyway, we can take a look at, say, thinking about a brick falling or something like that. If I look at a brick that was here and now later it's here, there's my increasing value of y. Here, the gravitational potential energy would be bigger than here. So as it falls, the gravitational potential energy will decrease, but it's picking up speed. So the y-coordinate decreases, gravitational potential energy goes down. But speed goes up, so the kinetic energy goes up. And it'll turn out that the sum of these two stay the same. So just like Joe and Jane's cash being a conserved quantity, energy is a conserved quantity, although here it's changing forms from gravitational potential to kinetic. So think of that as like two different wallets that we're sticking our natural money of energy in. In fact, we will so if a system is conservative, and that is an important if, the total mechanical energy, E, which is defined as the sum of the kinetic plus the potential, is a constant. And so then we can write that the final potential energy is equal to the initial. This allows us to analyze situations that could otherwise be a little gross. Like, for instance, again, let's say you are going and riding around on some loop-de-loop roller coaster. And you want to know, so we start you right here. There you go. Oops. At almost rest, because after all good roller coasters just barely get you going over at the top. So if that's the case, you can say that all of the energy of the system is potential energy. So I'm envisioning all of the energy we could possibly have as being fit in this bar, and then we can divvy it up however we want. Well, now let's say you end up at this location right here. Again, this is all the energy we could have, but now it's all kinetic. This is where you are going at your fastest. And then if, say, we look at some point like right here on top of your loop-de-loop, maybe it's something like a 50-50 split or something, right? Well, it is a 50-50 split. You're halfway up. And so since you're halfway up, the potential energy is half of what it was at the top of the hill, which means the rest of the energy has to be kinetic. So this is really awesome. It allows, assuming we can neglect air resistance and friction, it allows us to figure out how fast we're going at the top of the loop-de-loop without having to think any bit at all about how those forces are changing the speeds and directions and everything. So that is a taste of where we're going to be going with this. Now, let's say that a system is not isolated. What is that going to mean? A system that's not isolated is one that can still transfer energy with the environment. We weren't able to expand it broad enough to make it isolated. And so let's say this is my system here. you'll have a total energy, E. And it'll turn out that there are exactly two ways that we can transfer energy with the environment. We can either do work, which we give the symbol W for. So this is when a force is directly changing the speed of the thing in bulk, or the system can, say, push on a piston or something like that in order to push something along in the environment. So if we can cause a large-scale macroscopic movement of an object, either in the system, well, actually, be a little more careful. Yeah, if a large-scale macroscopic movement, either by the system or by the environment, is involved, then we can say that work was either done on or by the system. On the other hand, it might just be the case that what ends up happening is we have transfers between the individual atoms without causing any kind of a bulk change, a change in the bulk state of a system. In that case, usually we use the symbol Q and say that this is a heat transfer. And oddly, although physicists will often say heat, what they really mean deep in their souls is heat transfer. It's always this thermal energy in motion. So usually the way that we can write this then is that the change in energy of the system will be equal to work done on the system plus any heat transfers in or out of the system. These heat transfers we will worry about when we get to thermodynamics. Alrighty. So in the next set of videos, we will start to take a look at work and energy in more detail.